we can apply these principles of buoyant force to solve certain kinds of problems. Let's say I have a mass of 85 kilograms. When submerged, my apparent weight is only 5.7 kilograms by my volume, my density. Right? So first off, if I'm submerged, I'm underwater, swimming along or doing whatever, my apparent weight is 5.7 kilograms. Well, my apparent weight is really the net force acting on me. And, I should say my apparent weight. I'm sorry, my apparent mass is 5.7 kilograms, which means my apparent weight apparent, is going to be 5.7 times 9.8. Okay. And then what forces are acting on me? Well, we have gravitational force, and we have buoyant force. So we have, that's buoyant force going up, mg going down. Buoyant force is equal to the weight of the displaced fluid, which we've just determined is rho gv. I should say when submerged in fresh water. So that's rho gv minus mg. And so we can plug in numbers. 5.7 times 9.8 equals 1,000 times 9.8 times volume minus 85 times 9.8. And from that we can calculate what my volume is. And this works for any object if you can figure out apparent weight, which you can actually do on like a hanging scale sort of thing. Like if you have a hook, like our force sensors, those have those hooks, and if you hang something from a hook like that, you can figure out its apparent weight. It's the upward force needed to keep it from going down. And working that out gives us a volume of 0.0907 meters squared. And then the density, of course, rho of me. Density is just mass over volume. So that's 85 over 0.0907, which comes out to 937.155 kilograms per meter cubed. Is that realistic? I don't know. I mean, it seems like it would be somewhat realistic because we know a large percentage of our body is water, and water is 1,000 kilograms per meter cubed, so it makes sense that that would be somewhere around there. Now, additionally, you can, if you know this density of your body, you can figure out, along with your mass, you can figure out your body fat percentage, because the density of fat is about 900 kilograms per meter cubed, and the density of muscle and bone and such is more. It's about 1,100 kilograms per meter cubed. So using this, you can write a system of equations where we say that some amount of your mass is fat, and then some amount of your mass is muscle, but this would be your total mass minus x, and set that equal to the 937.155. We can use that to figure out what our body mass percentage is. So in this case, if I work this out, we subtract 1,100 times 85, 900x minus 1,100x gets us 200x. We can subtract off this 1,100 times 85. Error syntax. Oh, there's a parenthesis there. And that's a minus 92562, which is good because then our negatives cancel out. And x equals 462.814, and x was my percentage of fat. This was the amount of weight that is fat. So if we wanted a percentage, that would just be I guess that's So I guess my data for the problem was unrealistic because of my 85 kilograms of mass, 462 kilograms of it was fat, which obviously doesn't make sense. But this is a principle that they used with sort of a hanging apparatus to calculate body fat before we had the electronic body fat calculators like that, where they have the sensors built into the scales that work all that stuff out. Before they had that, they used this sort of procedure to calculate what someone's body fat percentage was. Another application of Archimedes' principle has to do with how objects float. An object will float if it displaces a volume of water or whatever fluid equal to its weight. Which is why objects less dense than water will float, because they'll displace a volume of water. If they're submerged, they would displace a volume of water that is equal to their volume, and that volume of water will have greater mass, and so they'll float. Whereas if an object is more dense, it will not displace enough water to make it the buoyant force greater than its weight, and it won't float. So if an object, to figure out an object's mass, if an object floats, you can just drop an object in a graduated cylinder and see how much water is displaced by figuring out the difference in the volume of water before and after, and that will give you the volume of water displaced, and using the density of water, you can then figure out the mass of the object. And for any floating object, you can always figure out its weight, because the weight of the object is equal to the rho of the object times the volume of the object times g. The weight of the fluid displaced is equal to rho of the fluid times the volume of the fluid times g. So the displaced fluid is equal to the weight of the object, so you can set, if they float, you can always set these two equal to each other if the object floats, and it's the volume submerged of the object. We can set these two equal to each other and use this to say that the volume of the object that is submerged is equal to the rho of the object over the rho of the fluid, and use that to figure out what fraction of an object will be submerged, and also use it to figure out the density of the object, depending on how much of the object is submerged.